for this class. Sorry. Oh, okay, yeah. So let's get started. Thanks for everyone being here. I know it's hard getting up Monday morning, so. All right, let's get started. We're on lecture 11, still on chapter 6. So on our schedule, we have to finish chapter 6 by Wednesday, and we're going to be on track still. And I think no class Monday, right, because holiday. I think schedule-wise we should be good if we don't have work on it. But I'll get to that later in announcements. So, all right, lecture 11, chapter 6. So agenda. We're going to kind of review velocity, potential, and stream function just a little bit more to kind of make sure we understand those concepts and how they actually connect and relate with each other. And then we're going to talk about basic plane potential flow, which you'll see is probably pretty similar to your Calc 4 class. There is things like source, sink, vortex, duple, things like that. So you'll see just 2D plane examples. And then hopefully we can get to the derivation of the Navier-Stokes equation. So I got some feedback. I will go over it hopefully towards the end of class. And I think majority of people said it's okay right now. But I did get some feedback and I want to account for everyone's comments. So some people are more a fan of less derivations and more examples. So that's why I put 3 in this lecture. Most of the derivations, if I don't find them too important, I will probably skip or kind of just breeze through. But things like the Navier-Stokes equation, you'll see eventually, but that's basically our equations of motion for viscous fluids, right? Because we've been doing non-viscous or inviscid. So I want to do like kind of a quick run through of the derivation for that so you conceptually have an idea of what's going on there. And that's important, right? Because if I just gave you the equations, for example, for like velocity, potential, and stream function, you'll just see a function that you're going to take a derivative of with respect to each variable. But in reality, right, it's a field of vectors that show your function, right, with each variable. So that's kind of the important concepts behind it. Okay, and then I thought maybe we'll get through content first and have announcements at the end. We'll just see. I just like to have something at the end to look forward to. So I don't know if there's something to look forward to, but maybe keep it more fun that way. So there's a campus safety announcement we can talk about at the end. I'd learned from meetings. And then midterm grading process. We'll talk about homework quiz on Wednesday. Sorry, when it says midterm feedback, that's like the feedback you guys gave me for the quarter. I have more quiz 2 graded. If anyone didn't get that, this will probably be the last day I'm holding on to them. And then project check-in if there's time. Any questions on agenda today? Good? All right, let's get to it. So breeze through this really quickly, right? We already learned what a stream function is. So this is just a copy and paste from previous lecture. Right, it's a need for a function and differential equation in 2D for steady incompressible flow, right? So here you have your U, nu, W, that's just your X, Y, Z direction. You take the derivative with respect to X, Y, Z. You have that in 2D down there. So only velocity in 2 directions in X, Y plane. These are your equations. You should already have that in your notes. Not gonna go over this again. Okay, that Greek letter is psi. So stream function is represented by Greek letter psi. Okay, velocity potential, quick review. They use, this is phi, this Greek letter, phi. So you'll see, right, they have the phi function with respect to x, y, z, u, v, w. Kind of similar to stream function, but I'll show in the later slides what's the difference between them and how they connect. Cylindrical coordinates are theta, z. So you should already have these equations in your notes, but don't forget this 1 over r here for that v theta, right? Okay, velocity potential. Here are just more equations. This is the equation we talked about just in vector form, right? Del operator takes the derivative in xyz direction. The main difference from velocity potential to stream function is, right, velocity potential is a consequence of irrotational flow. So this is coming from, that is zeta over there, your vorticity, right? And omega there is your curl. If that equals 0, it's irrotational. And that just means, right, if you have like those matches in the video I showed that's rotating, they're actually not rotating along that vortex, right? I went over that last lecture. This is just showing irrotational flow is satisfied. Skip through this because we already went through it. So this one is new. I believe we don't have much homework problems or examples of this equation. I just saw it in the textbook and it was in the other lectures too, so I thought I would just bring it up. Okay, so velocity potential to Laplace's equation for incompressible fluid. So the conservation of mass energy equation becomes this, right? So that's del operator dotted with your velocity vector. If you, right, put this, that's where that v comes from. Laplace is just 2 del operators. So then you see why there's a partial derivative. You take the derivative twice, basically, for Laplace's equation. X, Y, Z, cylindrical coordinates is right here. Like I said, I don't believe there might be homeworks when I checked on this, but I just wanted to put this on there just in case we need it in the future. Because you'll see, if you're reading the textbook for anybody, you'll see them refer to Laplace's equation. So this is here. Okay, then I made this is a good summary slide I made, right? This is just a T-chart of stream function on the left, velocity potential on the right. So you can kind of see how they connect, right? So in your problems that you're going to work through, I'll work through some, these u's are the same. So if you're working a problem, you can do u equals this, equals that, nu equals that, equals this. Same with VR and V theta. Right, and then concept-wise, the difference is velocity potential is from a consequence of irrotational flow. Stream function is a consequence of conservation of mass. Generally, velocity potential, if you need 3D, you have velocity potential for 2D stream functions, but you'll see in our example problems, we're mainly working off 2D. And another concept of how they're related, so you'll see in the textbook, they refer to this term called equipotential lines, and that's lines constant of phi. And it's weird in a textbook, they don't actually kind of explain what a constant phi really means. So I just have this in my slides, right? So it means your function does not change as you move along a specific line, like a streamline. So in your field of vectors, if you're trying to find your velocity vector, right, if there's a bunch of streamlines like this and you're trying to find the velocity vector tangent to that streamline, your function for either your phi or your psi, they're not changing, right? It's constant along those streamlines. That's what constant phi or psi means. And here conceptually, right, if you're finding a psi or phi, they're actually perpendicular to each other in your field of vectors. And that's kind of the main concept of how they kind of are related. And here you'll see some more kind of figures of how that works. So these points are the same, right? So flow around a bend here. You'll see your velocity coming this way. And then your equipotential lines are perpendicular, which is equipotential. It just means your phi, that's your phi function, right? That's constant. And then your psi here, these are your streamlines. It's either perpendicular. Same here, uniform flow. We introduced this vector, capital U. It's just your flow in a parallel. All your flow vectors are parallel. That's what uniform flow means. And you can see, right, these are your psis, 1, 2, 3. These are your phis, 1, 2. They're just perpendicular to each other. So here's another, even more repetitive. If it's at an angle, okay, these are your velocity vectors, capital U. So right, psi, that is going in the u direction. And then your phi here, right, your velocity potential is perpendicular to that. Any questions conceptually wise, how they're related? Main thing you got to think of is a question on the quiz or exam. Right, so this phi is your velocity potential, psi is your stream functions. The word stream goes with the flow of your velocity vectors. Phi is just perpendicular to those vectors. Yes?
I just want to confirm when we're saying constant, we don't mean a constant value.
No.
We just mean a function that's not changing.
Correct, yes. Okay, we're good there? Okay. So here we have some equations for uniform flow. So if this was only in the x direction, right, basically this is your equation down here, which is your phi is equals to u times x. U is the vectors, right? And then y direction, u times y. At an angle, this is your phi and your psi equation. So I would just write this down, this one, and that one. And like I said, I got the midterm feedbacks right. I'm going to save derivations for the Navier-Stokes equation. And conceptually, right, what does this slide really mean? We're not looking at a bunch of random variables we're just trying to solve for. So if your flow uniformly, your fluid is just going in the x direction, and right, uniform flow just means that these lines are parallel to each other. U is a constant velocity vector, okay? This is just the x direction and y direction. X and y are just coordinates, right, that you're plugging in. And then at an angle, here's that. Same thing, but you're just adding, this angle alpha. Okay. Sources and sink. So essentially, right, these hopefully are something you saw in Calc 4, I hope. So sources and sink, they flow radially outward or inward. So we introduced this new variable m, and don't get it confused with mass. It is a volume rate of flow spreading out from the line per unit length. So you'll see in an example problem I'm going to show, we'll do units for this m. And if you ever read math, this term per, right, that's a hint that you're dividing by something, right? So you'll see in our feature problem, they'll say volumetric flow, which is your Q, right? That's m cubed. That is your length cubed divided by seconds, right? Or volume per second. And they say per unit length, meaning you're dividing it by another length dimension. So I'll show you that in an example problem. I'm just saying, keep a heads up for this per. That means you're dividing by another unit length. So here in that equation, right, your velocity in the r direction, you have 2 pi r, circumference of the circle, is equal to 2 pi r times the velocity radius is equal to that m. You can solve VR for that here. We're working in polar directions, right? So we have our velocity in the radial direction and velocity in the angle direction. So since this is just going radially outwards or inwards, right? There's no angle. We're assuming v, nu theta is 0. And right, when we see these constants, they just mean that these functions are not changing, okay? And this is important as well. I'd write a note or just remember this, right? If your m is positive, flow is considered to be a source flow. If m is negative, the flow is considered to be a sink flow. So the example problem I'm going to show you later is a sink flow, so that is going to be negative. So this just means you'll have a negative right here for VR, negative m over 2 pi r. And then you can try the integral if you want, but if you just solve for your psi and phi, these are the equations that you get right here. So this is what you should write down. Okay, we're good. Okay, source and sink. Like I said, I'm going to save more of the derivations for the Navier-Stokes equation. But you can just see here, this is the equation you'll need if you combine a source and a sink. These are your variables, right? If you see this A a lot, that's just the distance from the center of the source and sink to each other, respectively. And then you have these angles, theta 1, theta 2, radius R1, R2 at a specific point in your field of vectors. And that sums up to this. And if you need these variables right, M is in the last slide here. That's M. I already pointed out A, I pointed out R, and then theta are these angles here. Okay, a doublet, I hope I'm pronouncing that right, it's not doublet. I think it's doublet. Correct me if I'm wrong. But it's essentially a source approaching a sink, and you're getting to A is very small. So you can say as A approaches 0. So now we introduce this variable K. And I was reading about it, and it was kind of interesting. It's like a mysterious, not mysterious constant, but the textbook just says K is a constant. They don't really go into details what the K is, so I had to do my own research about it. So this is an equation I found. Most of the time in your homework problems, this is either given or you're just integrating and you just keep it K. But here's an equation for it, just so I just hate having a variable in slides and there's no definition for it, right? So this M was defined earlier. It's not mass, right? It's that flow property. A is that radial distance between these two from the center, and right, pi is pi. And these are now your equations for your stream function and velocity potential for a doublet with that K constant. And right here is a figure kind of just showing that your source slowly approaching your sink. So you see all of these flow vectors, your field of vectors here, they're going out of the source into the sink, right? If you remember, sources are positive m's and sinks are negative m's. So if you do a problem, do not let that trip you up, right? Get your signs right. Don't get a small minus point deduction. Okay. Same thing here, just another look on the field of vectors there. Yes?
Could you go back to the previous equation? I couldn't finish writing it.
Oh, sure. Yeah, no problem. Okay, vortex. So I talked about this earlier, maybe 1 or 2 lectures ago, but here are the equations for it now that we have learned what these K constants are, what our stream function is, right, and velocity potential. And a vortex is just where your flow and your streamlines are concentric circles, right, which you can see here. And this is the opposite of kind of a source and sink. Why is it opposite? Right, because sources and sinks, they're radially outward or inward. These are just concentric circle lines. So, and now since it's the opposite, right, your VR is now equal to 0, and your V theta will now have a value. I keep using V and nu kind of interchangeably. I don't want to confuse you guys. Okay, if it's like supposed to be velocity, we'll say V. If it's supposed to be like dynamic viscosity or something, we'll say nu. So I'll just say v because it's actually supposed to be velocity. If it's a variable that looks like a v and it's not velocity, I'll say nu. Okay, so this is v. So right, v theta, we have vr. We already know what our k's are. Theta and r we know already. So here is a new equation, another Greek letter. Right, and it's weird, right? I don't know if someone's a Greek letter expert. This is gamma, but right, we have a gamma that looks like a, I don't even know how, like kind of like a bunny, right? It's like a, you know what I'm talking about? Gamma, right? Another Greek letter. So this is another gamma, and here we have a circulation, which is the strength of the swirl of your vortex. That is 2 pi times k. Right, k is your constant, which I defined earlier, and 1 to 2 slides ago. I believe this will be in your homework, this variable though. A lot of times this is also just a constant, because right, this is k is constant, 2 times pi keeps it a constant. This gamma keeps it constant. So I think some of your problems on your homework, you'll be take an integral, and then you just keep this as a constant. Yes?
What homework does this content fall under? Is it 5?
Should be 5. The one I just posted in the newest module. I believe it's 5. 6. I think, let's check really quickly. This is quick, and hope everyone's using the modules properly. Yeah, so homework 5. Yep. And I guess for anyone watching at home, if they're not here, or if you fall behind on content, right, how I've kind of been setting it up, I have it per week, and I would basically just look at everything posted in this module section for that week if you missed stuff. Okay. And this homework assigned for this week, right, that quiz will be for next week. Okay. And we'll talk about quiz on Wednesday in a bit. Okay, do first example. We're doing on time, 9:09. We're doing okay. So just remember these two equations here because we're going to be using this in the example. Okay, I'll let you read the problem and then we'll get started. Okay, it looks like the whole board is captured. Okay. Let's do, okay, we'll keep this little fox guy. I'd feel bad if I erased that for someone. All right. Okay, let's keep our good habits and follow Dr. Bridges, given and givens, assumed, and finds. So here, right, example 1, we have an illustration here of our quote-unquote tornado. Can be approximated as a free vortex, right? And free vortex just means irrotational flow, and there's no external forces or torque. If I'm blocking, so we have a strength of that is gamma, right? That's the circulation that I defined earlier. And if you have slides up on your computer, feel free to flip back and forward if you need those equations. RC, that's the radius from the center point to this inner circle here, right? Velocities measures at point A and B, respectively. You have those two values A and B. Determine the distance from point A, the edge there, to the center of the tornado. And we are given this distance 100 feet between point A and B. And then there's a written part that we'll just discuss. We're not going to fully write it out, obviously. But why can the free vortex model not be used to approximate a tornado for the flow field of R greater than or equal to 0? Okay, so givens, right? We have, that's gamma, right? Yep, that's gamma. Okay. We have our gamma. Is approximated. It's approximated with R is greater than RC. Okay, so RC is I guess we're calling this the radius core. Radius core. Okay, and then we have our VA equal to 125 feet per second. Is that dark enough for people? Need another marker? Is that okay? Okay. And then VB is equal to 60. Okay, that's our givens. Find the distance. Find the distance A to center of tornado. To center. Okay, and then assume we'll just do ideal flow. You can write incompressible flow, but when ideal flow is kind of considered incompressible flow already, and viscid flow. Okay, given, find, assume, nice and quick. We're good with that. Solution time. Oh, I don't like this marker. Let's make it get a darker one. Oops. Okay, now we have our equations I showed for a vortex last slide, right? So we'll just, this is new, but we'll just call it V for now, right? V theta equal to negative phi partial. Sorry, this is partial psi. Partial psi, partial r. Okay, this is equal to k over r. So let's just rewrite it, right? Okay, that was from last slide. So now we're just gonna plug in our values. So we have 125 feet per second and 60 feet per second, right? So we just plug in our velocities. So at VA equals 125 feet per second. We plug that in, we have 125 feet per second is equal to K, constant, divided by R. And like I said, from my physics 2 teacher, she had a good habit of every time you write a number, you write a unit. I will try to keep that up, but like I said, it's going to help you in the long run for that. So at VB at 60 feet per second, it's going to be 60 feet per second equal to KR. I'll put subscripts RA, RB here. Okay. We'll write out all our steps. So we solve, let's solve for K. So K equal to 125 feet per second times RA. This K is equal to 60 feet per second times RB. Okay. And then these two values are equal, right? So you can set these two equal to each other. So we'll do okay. Set those two equal to each other. And then you notice, given in our problem, RB minus RA is 100 feet, right? Looks like a V. Let me fix that. Okay. So now let's just solve for it, right? So let's do, yeah, should we just solve for it? So what I'm going to do, I'm going to move this term RB minus RA. So I'll move it over there. Why? Because I want to isolate it. So we're going to do minus. Okay, let's see here 1 second. Oh, actually, here's an easier way instead of doing this way. We're solving for RA, right? So here is a better way. Let's just solve this for RB. That's going to be plus RA. Okay, so now we plug in RB into here. I am regretting putting units every time, but it's a good habit. Sorry, I am going back from lowercase to uppercase here. Let's do uppercase. Okay, RA, 60 feet per second. RB, right, that's 100 feet plus RA. Okay, that is just algebra, right? So I will let you solve for this. We'll just do it in our head really quickly. Distribute, right? Move RA to one side, factor out RA, and then solve for RA. You guys can solve for RA from here, right? Okay, just algebra, okay? So final step here, you're gonna get RA, this is your final step. Let's skip some steps. Per second. Oh my goodness, my R's. No, it's not gamma, it's R. Make it nice and neat for you guys. Okay. So algebra, solve for RA. This is the value you should get. Right, and that's just distance from the center to A. You might ask, I don't think we used RC. Why? There is another part of the problem I didn't really like, so I blocked that out. That's why that's there, and that's why we didn't use it. We only did the first part. Any questions on this calculation part so far? Good, straightforward. Okay, and then it's asking, why can this free vortex model not be used to approximate the tornado throughout the flow field? And essentially, why is that? Is because, and a reminder, a free vortex means irrotational flow, and there's no external forces or torque. So, main reason is, right, if this is V theta equals K over R. Okay. And when I was reading the textbook, if you take the limit as R approaches to 0, why am I taking the limit as R approaches to 0? Because you want to find the velocity of the center of your tornado, right? So in division, right, you divide by 0, you get undefined. But here, if you're just taking R as it approaches 0, indefinitely really, really small, right, just fractions, this is going to make the velocity bigger as the denominator decreases. So technically, it's a limit approaches 0, but not specifically subbing in 0. So that just makes your V theta to infinity, right? And in reality, in the center of the tornado, where the radius is 0, the velocity is not infinity. So in short, that answer to that last sentence is no, because our V theta equation results to infinity velocity at radius equals 0, or as R approaches 0. So no. Okay, we're good? Any questions on that? Hopefully not too bad. And like I said, I'm always open to feedback. Anytime, let me know. Last week, I kind of hammered the concepts in one lecture and then, did examples at the second one. I probably shouldn't have done that. I think this is better. Just right after the slides, the equations I gave you, we do an example right after. So, okay. So this is a nice summary table of all the equations that I showed in the slides for each flow field scenario. Okay. Check the time. Okay. Okay, let's see if we can get to one more example and then we'll take a break. Okay, so these are equations, all summarized in a table, nice and easy for you, right? Uniform flow, it's just your flow vectors all parallel. Your source and sink, which is radially outward or radially inward, right? Be careful of your M, if it's positive or negative, right? So source M is positive, sink M is negative. I had the equation for what M is earlier. It's not mass, right? It's a flow value. Free vortex, we just used this example. and then double, right? That's as your source is approaching your sink. Here are the equations. Velocity potential, stream function, and then velocity components. Okay, nice summary there. Okay, so this is also, I think, in one of your homework problems. You'll see in the homework file, it says it's if we get to it. And I was thinking, oh, okay, maybe we can not go through it. But to get to the other concepts, this needs to make sense. So in summary, we kind of have to at least review it. So there's a homework problem on this, and this is kind of explaining what it is. So flow around a half body. So a half body, to get this flow, is obtained using superposition by adding a source to uniform flow. So our two scenarios, right? Our source is just our flow vectors radially going outward. And then our uniform flow doesn't specifically show here, but that's just our capital U parallel velocity vectors going in one direction. Okay, they're not crossing. So, and we just say half body, I believe, because we're only doing analysis on the front part, right? We're not caring too much of the other half, because something else happens there, which are different equations, so we're only going to focus on the first half of the body. Okay, start over here. Let's just look at the equation. So we have, that is psi, superposition, right? That's just fancy terms for you're able to add them together. So we have the uniform flow psi, and right, psi, that is your stream function, right? Plus uniform, plus psi source. These are directly just copied and pasted from the previous slides, okay? And keep track of this UR sine theta. This is going to come up in our example problem that we're going to do. And then here's our equation for phi, which is your velocity potential. And like I said, I hate having just an equation on here and you don't know what every variable means. So summary, U is your flow of vectors that are constantly approaching. R is the radius here. M comes from over here, right? This is your flow value. Theta is angle. And that should be all the variables. Yep. We already went over through this diagram. Here is the half body, right? So here is the stagnation point. And the stagnation point, right, we read in the previous lecture and example problems, that's just when your velocity equals 0. So at this very front part is where your velocity equals 0. This little circle here, because it explains the distances b, it was annoying because they didn't explain this in the textbook. This is just your source. And I think that's what the empty circle kind of symbolizes. It's the flow coming out of there for this half body. Okay, and why is that? Because, right, it's uniform flow plus source. So uniform flow is right here, these red lines. Source is right here. Okay, then you have your pi b, just distance from the center of your source to the edge of the boundary condition here. And you have psi is equal to pi bu on this, just on this boundary outside layer here of this half body. Okay. Any questions on that? I think that covers conceptually what it is and what our equation is. Right, in short, have these equations down, know what they mean. Yes?
I'm sorry, I'm not quite sure what B is measuring as linear distance there.
Yes, B is the distance from your stagnation point to your source.
And the source is inside the body.
Yeah, so I guess this isn't necessarily a solid. It's another flow. It's another, right, you have your uniform flow plus source. So there's two sources of flow and you're combining them in one scenario. So, sorry, yeah, to avoid confusion, this isn't just a hard rock or a solid. This is another flow. Okay, good with that? Okay, let's try to get through this example before break, and we'll take a break. We're doing great on time. So here, I think your homework does a good problem on, I think it might have been a source and uniform flow. So I did a different scenario so you have more variety. So this is going to be a steady flow and sink. So uniform flow here and a sink down here. This is, they call it a slit, so it's slightly different from a sink, and I'll show the difference of what it is. But yeah, take a read at the problem. Take a picture of this for people at home. And I guess that's one thing I got from the feedback a lot of people liked is I'm going through the effort of rewarding the people that are at home just by posting this stuff for them, right? But I give you guys some information, right, that for people that are here, just to reward you guys too a little bit after, right? So, okay, this is good. I'm going to erase this. Okay, erase this. Okay. 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 Steady flow. So let's read this together. Water flows over a flat surface at 4 feet per second, as shown in the figure below. A pump draws off water through a narrow slit, which is right here. Water going through there, at a volume rate of 0.1 feet cubed per second per foot length of slit. Okay, that's where this problem kind of tripped me up when I was doing it, I think yesterday morning. So like I said, this is volume flow rate, right? Because it's cubed per second. So I thought this was the unit, and I did the dimensional analysis at the end of the problem. I'm gonna giving a head start for us. This term per foot length of the slit, you're dividing this whole unit by another foot. So if you divide this whole unit by another foot, this becomes feet squared per second. And that is actually your units for your M that we have been talking about. I'm going to write that down, but I just wanted to verbally discuss it. Okay? Assume that the fluid is incompressible and inviscid, right? Incompressible, I've been kind of repeating it over and over, but incompressible density is constant. Inviscid means there is no viscosity in our fluid. And this can be represented by a combination of uniform flow, which is coming in this direction from your U, and a sink, which is right here. Okay, locate the stagnation point on the wall. And one thing I did not like about this problem, they use the wall and flat surface. This is, I just thought about it, this is the wall. Stagnation point is here, A. Okay? And determine the equation for the stagnation of the streamline. Okay, so given our U is equal to 4 feet per second, okay, Q is equal to 0.1. Depending on the time, I might set this problem up and we'll go on break because I want to give you guys a break. Feet cubed per second. Okay, so if I'm stating this now, you won't find this in other problems or in the text. Well, you see it in the textbook, but this, the M slit, right? That is just the flow value that we've been going off. This is not mass. this is given at 0.1 feet cubed per second. Okay, but like I said, this is tricky because it says feet cubed per second per foot. So that means you divide it by 1 more foot. Right, don't get your fractions wrong. You multiply by the reciprocal. So this is becomes feet squared per second. Okay, and then, so slit and sinks are different. So M sink is equal to 2M slit. Let's go back. I want to make sure you guys understand. Let's go back what M means. Where is M? Okay, right, so M be the volume flow rate. It's just the volume flow rate spreading out from the lines. So that's M here. That's the M I'm writing over here. So our equations are for the sink. We have a slit. So the volume, we call it volume flow. Yeah, volume flow rate is just, for a slit, it's 2 times the value of a slit for the sink. So that's the only difference of solving these problems. Like I said, if there's something like this on the exam, I will obviously tell you. I'm not going to give you a problem that we have not seen or done. Okay? So reminder, right? M is volume rate of flow spreading out. And right, keep track of the positive negatives because that's going to affect our, I guess tell me now, if we're a sink, are we going to be positive or negative? Negative. Okay, perfect. So we're going to see why that's negative. Or that is why it's negative. Okay, we'll just go here. Same problem. This is just a different figure showing more of the variables. Okay. Okay, so then we're going to do find stag point at A. To the right of the slit. Right, A is listed there somewhere. Yep, right there, to the right of the slit. And so we're just basically going to be solving for this RS. We're not looking for a velocity. We want to find the distance from here to the stagnation point. So we're just looking for that radial distance there, that R. So, in short, RS. Okay, find. Assumptions will be the same. Oh, and then we could do another one here. Uniform flow plus sink. You can add them as superposition. Let's look at the time. Okay, let's do, before we start this problem, let's do like a 7-minute break. We'll be back at 9:52. That way, I think we might go past break for this problem. So, okay, we'll come back 9:52. And if there's group questions for a project, let me know. I also want to get all kind of the project ideas down soon, if you have them. Okay.
Stayed up late last night and just didn't show up. I stayed up late last night. Those guys guys could not hold the ball to save their lives.
It's actually frustrated that the NFL website didn't have the actual hours to vote for the kicker for the game. Yeah, they added it like a week after he got in record.
Anyone know what other classes you're taking are again for this quarter?
And every time I looked at it was just like it would cut to some guy like when the ball
Oh, okay.
that game was like
390 statistics. 112. It's like the Python class. Is Professor Johnny Lin still teaching that one, or someone else?
But we have someone new right now taking that.
I mean it's still there was like
Okay,
I
gotcha.
took it with Lynn last year.
Okay, I had Professor Lin, too. He was awesome. Yeah, that's good. Just curious. I hear you guys talking about your questions and projects. Like, I wonder what classes you all are taking. So, do you all feel it's like a big step from your sophomore year? It's a lot harder. Okay, I see. Gosh, okay, that should be good.
She decided it's way harder than she decided like do this.
The homework is like harder, but there's less.
Okay, yeah.
Like literally feels like when you I was like and you see those videos of like engineering classes like take 5 hours per problem.
Yeah, it's like 5 hours per problem, but
Right.
there are only like 5 problems per lesson.
Right. So that,
Our guys in Munson really spent like 3 days on it.
yeah, I remember that's what my non-engineering buddies didn't understand. It's like, Elijah, let's go out. Like, I was like, no, I have like 4 problems to go through. Like, yeah, there's just 4. Let's go out. And it's like, no, I can't. It's like 5 hours per problem. Yeah.
They always ask. Why did they disappear? That's kind of my roommate.
You have to like guess what you have to put in. Like you'll have an answer and it's like how do I put it in?
Once my roommate was like complaining about something, and then he was like, "Oh, what do you have?" And I was like, "Oh, I have this."
Yeah, because I can answer it. I can do
Oh man.
That sounds cool.
45.
Yeah, I mean, as long as you find an equation from class that works with it, then yes.
Doesn't bring it back to the world.
Two people, 70 one appetizer and one meal.
Not really. I mean, there's a slide, but then we have
Well, they used to be dollar tacos. That was the $1.50 taco. So now it's like, oh yeah, that's full size.
half of what I'm doing. So I have like 2 reports per week.
They have real room
Because like I guess your audience yeah.
Yeah, I mean, because you just did the double surprises like I saw the rate of fusion cameras and not the sports.
I heard someone behind me.
So we were playing this like by the morning, so the guys would all go play like Warhammer, and then you get like 5 to 10 Warhammer players every order to the thing. If we fill up the store, buy as much as we could, then we'd go back and change of management. They fired all the staff. One of the guys knew me because I would come to the mail service before the change of management.
I mean, how